Hello, everyone. My name is Kaiyi Yuan, and I'd like to introduce networking in the operating system as my final presentation. From the user perspective, networking is as simple as calling send or receive function. But behind the scenes, the operating system handles a complex stack of protocols and device interactions. Networking in OS is a hidden but critical subsystem. The operating system plays a critical role in moving data through complex layers, from your program to the network card. For example, some operating systems are designed as components of distributed systems. In this case, the internal modules of the operating system need to communicate with the kernel modules of other hosts over the network. For example, Amanda Plan9 match distributed kernel. This operating system internal modules communicate using RPC protocol. Then the kernel updates, model loading, and other operations rely on the network too. Then the network protocol stack, such as the TCP/IP stack, is part of the operating system. It participates in packet forwarding and filtering through NetFilter protocol hook, and it handles interrupts, routing, data segmentation, and reassembly, and so on. In this presentation, we will take a simple client program in C as an example to show how networking really works in the Linux kernel mode. The function below are system calls used for network communication in C languages. They are often used in client programs to connect to the server and communicate data through the TCP protocol. The socket function creates sockets and return a file descriptor. Connect function establishes a connection between the client and the server. Send function sends messages to the connected server, and the client receives messages from the connected server through receive function. These functions trigger system calls into the kernel, and kernel allocates socket structures and buffers, which marks the beginning of the journey inside the OS networking stack. The socket lifecycle in the kernel starts with socket, then connect, send, receive, and close functions. The kernel maintains data structures to track each socket's state, buffers, and protocol control blocks. The graph at the bottom right corner shows the establishment of TCP connection, which is called three-way handshake. The sender sends its SYN code, trying to connect with the receiver. After getting the message, the receiver sends its SYN code and ASIC code to tell the sender that it is okay to connect and ask, "Can you hear me?" If the sent gets a message from the receiver, it sends its ASIC code too to show that it also is okay. Once the receiver gets the ASIC code from the sender, the connection is established. Later, I will show you this process with some tools. Here's how the data flows through the kernel. From the socket layer through the TCP transport layer to the IP layer, then to the link driver, and finally to the hardware. This modular design allows each protocol to function independently, but in a layered fashion. Let's walk through the entirely actual data path. Send function passes the data into the socket's send buffer. TCP then segments it. IP adds routing information, and the driver queues the frame for the transformation. Finally, the NIC puts the data on the wire. To track details, we can use some tools like strace to show the system call, and TCP dump to show network packets, and so on. Now, I'd like to introduce three key concepts in kernel network. The first one is socket buffers. The struct skbuff is a kernel structure for networking. Buffers are used for flow control, retransmission, and ordering. If buffer full, send function will block or return in E again, unless it is in non-blocking mode. These buffers help controlling flow and avoid data loss under high load. This is a structure of skbuff. It contains packets buffer management, contains protocol information, the device and routers, a protocol stack pointer, its head pointer, and the linked list management pointer. Second one is zero copy networking. In traditional paths, it involves multiple memory copies, while in a zero copy methods like sendfire, it eliminates the intermediate copies between user mode and the kernel mode. It also reduces the CPU usage and boosts the throughput. There are four kinds of zero copy methods, and in different scenarios, we can choose different methods. For example, if we transport files in the kernel network, we can use sendFile function. If we transport messages based on socket and socket forward, we can use splice. To process data, we can use mmap and the write function. And to pursue the ultimate performance, we can use different NIC offload function. Thirdly, is a topic about interrupts versus pooling. In old NICs, each data packet would invoke an interrupt, and it has no batch processing capabilities. While in a new API, in an API, it uses a hybrid interrupt plus pooling and dynamic adjustment mechanism, which boosts performance in high throughput environments and reduce CPU usage. All right, now I'd like to show you an example of TCP client and server to track details during data transmission. First, there is a client.c file. We first define a port 9000 as a server port, and we define a message hello from the client to see the details that, from the client to the server. The code uses a socket to create a socket connection. You then set a server address with your own localhost address. Then use connect function to connect to the server, send message with send function, and receive response from the server using receive function. And finally, close the socket connection, use close function. Then in the server.c file, It also use socket to create socket and bind the socket to the server port 9000 and use listen function to listening on this port and use a while loop to keep the server running and use accept function to accept the connection from the client, read message through read function to read message from the client, and use the write function to send the reply hello from the server to the client and close the connection by close function. Okay, let me show you the whole process. The first step is to combine the client and server. This step I have completed it, so I will start at step 2. First, I will wake up my virtual machine. Oops. Okay. In this demo, we need 3 terminals. And step 2 is run the server in the terminal 1. And we run the server. The server is started and the server is listening on port 9000. Step 3, run TCP dump in the terminal 2 to monitor the data packets that are about to send. In terminal 2, we did this for my password. The TCP dump is started and it continue listening the port 9000. And in step 4, run the client with trace in the terminal 3 to track system calls that are related to network. Okay, we can see many results here. The first one in the server, we have received hello from client, which means the client has sent a message to the server and the server received this message, which means the TCP connection has been established successfully. And what TCP dump captures in the terminal 2 are real network data packets at the Linux kernel. The first 3 packets shows the establishment of TCP three-way handshake. We can see there are many information and from this to there, each information is a single data packet. And this is the first one, first packet. We can see the SYN code is this number and it is from the client to the port to the server port. And the second package is from the server to the client. And the ACK code is this, which is 1 greater than the SYN code of the first packet, which means the server has get the first packet from the client and the first handshake is successfully established. And the second handshake also established successfully. And in the third one is from the client to the server. And the ACK code is 1, which is 1 greater than 0. It also means the third handshake also established successfully. And in the fourth package, we can see here the sequence, the SYN code is 19. Why it is 19? Because the length is 18. 18 is what? 18 is this. Hello from client. There are 6, 11, 18 bytes. So the length is 18. And in this packet, the length of this packet is also 18. What is this? It is this server's reply. Hello from the server. Yeah, we can see it is from the server to the client. Yeah. And what trace tracks are system calls in the process of user mode calls into the kernel mode to complete the data transmission. We can see the socket, the connect, the send to, the receive from. They are all system calls during the transmission from the user mode to the kernel mode. Okay, let's go back to the slides. You can see the example results, and the final results is here. I have shared the codes on Piezo, and if you are interested in this small demo, you can run it on your Linux or even improve it. For example, you can get the input from keyboard as a sending message to the server, or try to run this program in a multi-threaded environment. Okay, in summary, sockets are just a thin layer over a rich kernel subsystems. Tools like Strace, TCP dump, and TC can review that logic. There are also some advanced topics that are not included in my presentation, like netfilter, IP tables, eBPF, which is in-kernel packet tracing and filters, and DPDK, user space networking for ultra high speed. All in all, networking in the OS kernel is sophisticated and performs critical subsystem. Understanding how data flows from applications through the kernel helps us write better programs and troubleshoot complex issues. Okay, that's all about my presentation, and thank you for watching and listening to this. If you have any questions or want to discuss this topic with me, feel free to leave your comments or email me. Thank you very much.